Okay, good. Very good morning to everyone. Thank you for joining us for the last installment of this year's Encrypt Public Seminar Series. The NUS Center for Research in Privacy Technologies, or Encrypt for short, is happy to have you with us this morning as we showcase our research and expertise in emerging privacy-preserving technologies and issues through this seminar series. For those who are new to the center, Encrypt is a strategic capability research center in privacy-preserving technologies. It aims to spearhead research in three core pillars, namely privacy preservation along the whole data lifecycle, privacy preservation for data with emphasis on unstructured data, and privacy risk management. For more information on the center, do visit our blog and website, which is displayed on the screen as you see now. So today's speaker, Professor Brian Law, is Associate Professor at the Department of Computer Science of the National University of Singapore and the Deputy Director of AI Research and Technologies at AI Singapore. He is also a Principal Investigator in Encrypt. His research interests include probabilistic and automated machine learning, planning under uncertainty, and multi-agent robot systems. Today, he'll be presenting his preliminary research effort in trusted data sharing. During this talk, we request all of you to kindly mute your microphone and keep your questions for the end for the QA session. So without further ado, I request Professor Low to please present his work to us. Professor Low, the floor is yours.
Yep, thank you. Let me share my screen first. Okay. Let's see. Right. Thanks for coming. So today I'll be talking about trusted data sharing. Specifically, I'll be focusing on two aspects of our work. One, which is to incentivize collaboration, right, between multiple parties who wants to build a better model. And the second one is the part where we are thinking about how can we have the rights to be forgotten, right, in machine learning. Let me first talk about the incentivizing collaboration. Okay. Right. So in this work, right, on collaborative machine learning, this is published this year in ICML 2020. It's work that's done by my PhD student in her first year, right, together with Ye Hong Zhang and Man Chun. So in this line of work, you are going to see later on that it integrates three different aspects of knowledge, right? One of which is information theory. You're going to see cooperative game theory as well, right, being involved, not surprisingly. And finally, machine learning. How can we integrate these various aspects of knowledge together, right, to make this work? Let me first talk about the motivation of the problem of our interest. Now, a motivating application is as follows, right? Imagine that we have three hospital clusters, right? Like, for example, in Singapore, we have NHG, SingHealth, and NUHS. They may be interested in accurately predicting the progression, right, of diseases such as diabetes. Now, as they have limited data on their own, right, they can only produce models with limited predictive accuracy, right, as you can see here. Right? Now, these hospital clusters can work together, right, by sharing their data with a trusted central party. For example, this can be a government agency like the MOH Office for Healthcare Transformation, which is MOHT, or Integrated Health Information Systems like IHIS. And there'll be parties that are interested to enforce this kind of collaboration. Now, with the aggregated data, we can train an improved model as a reward for each hospital cluster, right? In short, I'm going to call this the model reward, right? Or put differently, it's just a model as a reward, right? Now, what's the key perspective of our work here? In this slide, I'm going to motivate why we are doing that. Now, to encourage collaboration, the key perspective is that a hospital cluster, right, which contributes more valuable data, it should get back a more valuable model, all right? A hospital cluster which contributes more valuable data is going to get back a more valuable model, right? We are going to define what valuable means later. Now, the central party then gives each hospital cluster a model reward, which can then be used for unlimited future predictions by themselves, okay? Now, some of you may ask, why is it that we consider this perspective where if you give data, we are going to give you back a model or an improved model, right? And not talk about money, right? Money is, after all, the most important thing to us, right? So in other words, like, why not compensate each contributing party with money instead, right? Now, there's a Chinese proverb that goes like, talking about money hurts a relationship, right? So in particular, the multiple parties or the central party, they may be unable or unwilling to involve money in the exchange due to legal or practical restrictions. As an example, think about startups or SMEs. The one thing that they definitely don't have is money, but they have plenty of manpower to help you to collect data, right? That's one reason. Another reason is if you're talking about money, how much is enough, right? And where do you get the money from? Even if the party truthfully reports, right, its cost of data collection, now other parties may question, is the data really worth that much to the others, right? Now, finally, a final reason is that there are certain entities that are more interested in obtaining an improved model than selling the data, right? Think about the hospitals in this case, all right? And as a result, right, in this talk, we'll be looking at the fact that if you give data, I'll give you back an improved model, right? As compared to your own, okay? Now, there may be other motivating use cases, right? For example, you can think about precision agriculture, where each of this party represents a different urban farm or vertical farm. And the central party would be someone like the Singapore Food Agency, right? As another example, you can think about mobility demand for taxis and Grab, right? Where each party corresponds to a certain taxi company, and the central party could be LTA, our Land Transport Authority, all right? So now this is the overall motivation. Now, to reiterate what I've said previously, right? In any general setting, now individual parties, they have limited data and can build higher quality machine learning models from working together or from collaboration. Now, however, as they have incurred costs to process the data, they need incentives and rewards to participate. We desire fairness, right? In the following form, we want to receive higher rewards, right? In the form of a model, if we contribute more valuable data, right? And like I've mentioned just now, we are looking at the case of non-monetary benefits, right? Because money may be unavailable, the payment, like I've mentioned just now, it can be debatable, right? So in this case, we have a non-monetary incentive scheme. Now, it is practical to give out models as rewards, or I call them model rewards from now on, right? As there are parties who care more about the prediction. Note that unlike money, what's interesting is that this model reward is freely replicable. What that means is that you can reuse the same data, right, to train a better model for more parties without any additional or marginal cost, all right? So in this line of work, you're going to see that this red box highlights our key contributions, right, which distinguishes our work from the others. Now, we ask ourselves three fundamental questions in this line of work. The first question is that of data valuation, right? How should we value parties' data, right, before we can even reward them accordingly? Then the second question would be, how should we design a reward scheme to decide the values of the model rewards, right? In order for us to incentivize a collaboration, right? What incentives would encourage people to collaborate, right? This reward scheme must promote or provide this form of incentives. Now, in this work, we consider adapting cooperative game theory concepts to define incentives, right, beyond fairness that I've mentioned just now. Simply because, for the model rewards that we have, they are freely replicable. Now, we then propose a non-monetary reward scheme using a parameter to trade off between incompatible incentives while preserving fairness. You're going to see that later. Now, after we have decided the values of the model rewards, the last question is, how do we realize them and train the models, right? So we're going to answer these three key questions, right, in this talk and in our paper. Now, we're going to start by answering the first question about data valuation. To measure the usefulness of data and quality of the model, we'll most likely think about evaluating the performance on a validation data set, right? Now, however, in reality, it is hard to agree on a validation data set, as all these different parties, they have preferences that vary. And also the future test queries that they may have, they may differ from the current validation data set. Now think, for example, the hospitals, they have patients of different demographics, and this may even change in the future, right? So what we propose here is to use an information theoretic concept, right? Now which we call information gain, right? Now the value of a coalition, right? A coalition is simply a group of parties, which I denote by C here, right? Is the information gain on the model parameters, right, denoted by this neural network. Now, examples of model parameters would be the weights of a linear regression or the weights of the neural network. And we are looking at the information gain on the model parameters, right, given the data from coalition C, all right? So you can imagine that if, maybe I'll explain next, right? So you can see that, or from here, what's going to happen is that if you have more informative data, right, if you have more informative data, that will lead to a greater reduction in the uncertainty of the model parameters, all right? Now, this will increase weights on parameters that are more likely, right, given the data, right? For example, that of the true parameters. And as a result, it improves the predictive accuracy in expectation. So what you can learn from this is that a higher quality and hence more valuable model can be trained using more informative and valuable data, right? A higher quality and hence more valuable model, it can be trained using more informative and valuable data, all right? Now, by choosing information gain as the data valuation method, we can have a very interesting property, which we are going to use later on, which is the case that if you add more parties or more data, it can only increase the value, right? Increase this value, right? Now, this information gain is, it also accounts for other aspects. For example, if you have noisy data, then the data is actually less informative. Or if you have redundant data, which you're going to see later on. For example, another party has very similar data as you, right? Then your data is going to be less informative, all right? So I'm going to use these two words interchangeably when I refer to data, right? Whether they are more informative, that means they contain a lot of information, or they're more valuable, all right? Okay, now we're going to move on to the next question, which is about the designing the incentives and the reward scheme. You're going to see later it will make use of the data valuation method. And this is, of course, the focus of our work. Okay, now I'm going to give you an overview of the procedure, right, of this incentive mechanism. And later on, I'll go into the specifics. Now, the central party, the trusted central party, which is the one on the top left, right, it will value the data of each party or coalition of parties and compute this thing called the Shapley values, right? And I denote it by phi, right? Like this is party I, this would be phi I, party J, phi J. Now, Shapley value is, intuitively, Shapley value is like the expected marginal contribution, right, of that party, right? And I'm going to talk about that later. Now, for fairness, The central party then uses these Shapley values, right, to decide the model reward values, which I denote by Ri and Rj, right? Like what's the values of the model rewards that they will receive, okay? Then next, right, to realize this values, right, the central party will then need to select or derive data from the aggregated data, right, from all the parties, right? And for each party, different data is selected and used to train a different model reward depending on their contributions, okay? And we're going to elaborate each step, including the Shapley value in detail next. Now let's go into the incentives. We prefer a collaboration that involves all parties in the set N, right? We call all parties, or we denote it by the set N, because this will lead to the largest aggregated data set, which gives you the highest possible model reward with the aggregated data set. And in so doing, we kind of eliminate the tedious process of deciding whom to collaborate with, right? And we involve everyone. So this is what we call the grand coalition, right? Where every party is involved. Now we're going to look at each of these incentives in turn. Now what I can say at first is, of course, perhaps I give you an intuition to each of these incentives of why people would want to, or different parties would want to come together to collaborate, right? Before I dive into the context. So as an example, feasibility, right? Now, it will be quite a handful of words here, but I'm going to tell you what each means in turn. Now, for feasibility, think of the following. You know, if you get back a model as reward, it cannot be better than a model that that trains on everybody's data, right? If that happens, then you're kind of creating additional data, which is not possible. All right. Therefore, as you can see here, right, the model reward that's going to be received by each party, it cannot be more valuable than the model trained on the data of everyone's data, or the data of everyone. All right. And this is what we call feasibility, because if you somehow come up with a mechanism that says that the model you receive is more valuable than all the parties put together, then something is clearly wrong. All right. Now the next one is efficiency, right? Efficiency. In other words, we don't want to waste data. Why is that the case? Now we want the case where, you know, for some party, the model that it receives as reward is at least as valuable, right, as the model that's trained on the data of the grand coalition. Now, why should we think about this? Now, some of you may ask, now, if I can train a model that's based on everyone's data, now, who's going to receive that one, right? Later, we're going to answer that question. Now, if you don't give some party a model that can be trained on the data of the grand coalition, that means some data has gone to waste, right? That's something that we don't want. And if no data goes to waste, this is the aspect where we call it efficient, right? Now, the next one is what we call rationality, right? Now, it's a rather simple concept, right? What you can think about is the following. Now, compared to the model that you train on your own, you would like to receive a model that is at least as valuable, if not more valuable, right? That makes sense. Otherwise, why would one party want to go into a collaboration, right? So that party is said to be rational, okay? Now, if every party is rational, then you can see that they prefer to collaborate instead of working alone, all right? Now, what's interesting up there from R2, R3 to R4 is that for R2 and R3, right, feasibility and efficiency, we needed to adapt them from cooperative game theory, right, because of the notion of this freely replicable model rewards that we have, all right? And as a result, they are modified from that, right, instead of adapting exactly, okay? Now, the next incentive, it will be more interesting, right? Because this is the part where we look at fairness, right? Now, fairness is, you know, we are going to be inspired by the fairness concepts in cooperative game theory. Now, essentially, this fairness incentive captures the key perspective of our work here. What's the key perspective? Remember or recall that the more informative or the more valuable the data, the more valuable, if you provide more informative or more valuable data, then the model that you receive as a reward will be more valuable. All right. So for fairness, all parties model rewards, they have to satisfy the following properties, right? So again, I'm going to go through them intuitively first to let you understand what they are about before I dive into the context, right? What's uselessness? So that means that if the party provides no, not data that's of no value, that means that is not informative, then it is a useless one. As a result, it shouldn't receive any model as reward that is of value, right? So we need to ensure that this is the case. Otherwise, some party is going to benefit, right, by providing junk data, right? Now, how can we say that the party's data is not informative, right? Specifically, if you take a look here, it means that it does not improve the quality of the model, right, trained on data of any coalition that we form, right? As an example, the party has no data, right? In this case, it receives model reward of no value. Now, the next one is what we call symmetry, right? Symmetry is the case where if both parties, their data are equally informative, right, or equally valuable, then they should receive equally valuable model rewards, right? That's very intuitive. And how do we know that their data are equally informative? If you look at their data, when you include the party's data, right, it yields or gives the same improvement as the other party's data, right, in the quality of the model that's trained on data of any coalition, right? Then in this case, both of them should receive equally valuable model rewards. Now, this next property is also quite interesting, right? We are comparing between two parties. We are asking which party is more desirable, right? And the intuitive answer is that the party with more informative data, all right? So if one party has more informative data than the other party, then we are going to reward that party with more valuable or informative data with a model that's more valuable, right? That sounds fair, okay, which is our key perspective. So how do we know, right, that the party has more informative data? And again, you can see from here, now when you include this party's data than the other parties, right, the quality of the model trained on the data of at least one coalition, right, it improves more, right? In other words, this party is able to improve more on at least one coalition compared to the other party, right? In this case, we expect this party, right, to receive a more valuable model as reward, all right? Okay, now the very last property is something that is very useful as well. Now, this will actually encourage a party to contribute data of more information or more value, right? Now, what it says here is that if a party so chooses to contribute data that's more informative, then it should get back, or she should get back, a model that's more valuable, all right? Now, again, we can ask the question, how do we know, right, that the part, or how can we tell that the party is adding data that's more informative or more valuable, right? And this is the case here, right? If the quality of the model trained on data of at least one coalition that contains this party, if it improves, right, when that party provides a more informative data. Now, everything else being kept equal, then in this case, she should receive a more valuable model as reward, okay? So these four properties sum up what we mean by fairness. Now to reiterate, if a party is useless, we shouldn't reward them anything good. Now, if two parties provide data of the same value, right, then we should reward them equally. Then the third one, desirability, which party is more desirable, right? In this case, we're comparing now. If one party provides more informative data, we should reward that party with a more valuable model, right? Or a higher quality model. Last but not the least, right, it encourages a party to provide data that's more informative, right? For example, by including more of its own data. Now, if it does so, then it's going to receive a more valuable model as reward. Now, each of this that I've mentioned here, even though they are in words, you're going to see in the paper that it can be translated into some mathematical expression, right, to describe them, right? So if you want to know the mathematical details, I refer you to the paper. But I would say they're harder to understand though. Yeah. Okay, now, previously, you have seen these 4 properties that constitute the fairness incentives, right? So the model rewards that every party gets, they should satisfy all the 4 properties. Then they they receive this fairness incentive. All right. Now, in fact, the properties of the last 2 properties, which is that of desirability and monotonicity, right? They imply that for a party I, right, for a party I, its marginal contribution to any non-empty coalition C, they matter, right? They matter. Now, what's the implication? Now, what it says is the following. If this party I has a small value of data on its own, as an example, it has very few data points, but this party can still be highly valuable to the others in that coalition C if her data is unique, right? In other words, the other parties don't have data of don't have the same data as party I, right? The data is unique, then it can still be considered as highly valuable, right? Using marginal contribution. Right? Now, another implication, right, is that if a party I has a high value of data, right? Even though it has high value of data using information gain, now, using marginal contribution, she may still be less valuable to the others because the other parties may have very similar data, right? So if there are some other parties with very similar data in the coalition, then the marginal contribution of this party is minimal, right? And hence less valuable. So now, like some existing works, right, we choose to use this notion of Shapley value, right? It corresponds to the expected marginal contribution, right, which is computed here because the marginal contribution is of this term. Notice that it comes here, right? And you take an expectation or an average over it, right? So that's why it's called the expected marginal contribution of a party when it joins the parties preceding it in any permutation, right, of n. Now, why are we interested in this? It can be shown that using this Shapley value is satisfies, or using this Shapley value as model reward, right? You're going to see later. It can be shown to satisfy all the fairness properties. All right. Now, from now on, right, we're going to abbreviate this Shapley value as phi I, right? So if you see phi, it corresponds to Shapley value. Now, this phi can actually be replaced by other fairness concepts that satisfy the properties that I've mentioned earlier, right? There are some other fairness concepts that do, besides Shapley. Okay, now I've talked about quite a few incentives. The next two, right? Among the next two, the first one would be that of what we call stability, right? Now, previously we mentioned that we desire the grand coalition, right? Which involves all parties. Now, we are going to discuss the condition needed to assure that no coalition or subgroups, right, of parties will agree to leave because they can find higher reward somewhere else, right? If no coalition of parties of such form exists, then we know that the grand coalition is stable, okay? Now, the adapted condition that we have from cooperative game theory is as follows, right? The model reward that's received by some party is at least as valuable as the model that is trained on the data of the coalition that it belongs to. Now, if it's at least as valuable, there's no reason for this party to leave, right? And that's how it achieves stability. Now, from the above, we can in fact have a simplified way to check, right, whether this is true. Now, how do we check it? Now, for each party, the model reward that it receives if it is as valuable as the model trained on the data of the coalition, that includes all parties with smaller or equal Shapley value, then we are done, right? And with this simplified check, right, it reduces the number of constraints that we need to check, right, from exponential in the size of or the number of parties involved to one that's linear, because we just have to go through each party in turn. Okay. Right. So unlike the previous incentives, stability is just an optional incentive condition that you can choose to include or not. Depends on whether you want the grand coalition to be stable. All right. Now, the last incentive that we're interested in is what we call the group welfare, right? And it corresponds to the total value of the model rewards over all parties in the grand coalition, right? Or put differently, you just sum all the model rewards. Now, the hope, of course, is that this reward scheme can maximize the sum of the values of the model rewards. However, in this work, if we try to do that, you can imagine that some party may actually receive less, right? So this is an incentive that we try to do our best, right? By increasing as much as possible, right? Instead of being able to fully maximize it, right? So if you want more details about these different incentives, please refer to our paper. Now we are ready to build up our reward scheme. Later, we'll show that, through this reward scheme that we have built, it is going to satisfy all these incentives that we talk about. And for the last one on group welfare, it is of a varying degree, all right? Now let's start simple first, right? We are gonna start from the fair solution, where we set the value of the model reward simply to the Shapley value that I've discussed earlier, all right? Now this is a fair reward. However, it has some problems, right? It does not satisfy one of the incentives called efficiency, because if you do this, right, the total value of model rewards is the same as that of the model trained on the data of the grand coalition, right? But remember, in efficiency, what we really want, right, is that, there exists some party whose model reward, right, the value of it is the same as the model trained on everyone's data, right? So clearly this is not satisfied, all right? So now, in fact, since the model reward is really replicable, we want the total reward to instead exceed, right, that of the model trained on the data of the grand coalition, okay? So let's look at, or let's revise it so that this efficiency incentive can be satisfied. Now, instead of setting the rewards to be equal to the Shapley value, we can consider setting it to be strictly proportional, right? Strictly proportional. Now let this phi star be the maximum, be the largest Shapley value that we have, all right? Largest Shapley value, that means the party that, after calculating, it has the largest Shapley value. And this V of n to be the value of the data of the grand coalition, all right? Now with this scaling, right, this scaling of phi I, or the Shapley value of party I, you're going to see that the model reward that's received by the party with the larger Shapley value. That means replace phi I with phi star, right? That's the largest possible Shapley value that you can receive. Then you can see this whole term cancels away. So the model reward that's received by the party with the largest Shapley value is going to be as valuable as the model trained with the data of the grand coalition. All right. And as a result, right, this efficiency incentive is satisfied. Okay. Now, however, for other parties with smaller Shapley value, right, those who have smaller Shapley values, these may not be generous enough, right? And so you can see that we have given an example in our paper, right, that the model reward received by a party with smaller Shapley value, right, it may be less valuable than the model that it can train on its own data, right? As a result, it doesn't satisfy the rationality incentive. Now we're going to try to fix this next by increasing the model reward, right, for parties with a smaller Shapley value. Now our trick is actually to introduce a trade-off parameter called rho, and rho ranges between 0 and 1. Now, when rho is 1, right? When rho is 1, we're going to obtain the previous Shapley solution, right? When rho is 1, then it corresponds to the Shapley solution in the previous slide, okay? When rho is 0, right? When rho is 0, then you can see this entire term disappears, right? Entire term disappears. And every party will receive as a model reward, right? The model that's trained on everyone's data, all right? Regardless of that party's contribution, right? So, you know, some of you may see this as you know, equality, right? Because every party, regardless of what they contribute, they are going to get back exactly the same or equal model, all right? And but clearly, this is not fair, right? This is not fair because if we want, if some party contributes more data, we want to reward that party more, right? In this case, if we choose rho to 0, then regardless of the contribution, every party gets the same model, right? Now, even though it's unfair, it's going to satisfy both rationality and stability, right? Because rationality, because if every party gets the same model that's trained on everyone's data, it's clearly not going to be worse than its own model, all right? Now, why stable? Is because everybody gets the best possible model, right? There's no reason why they want to form another coalition, all right? Now you can see that if you try to vary between these two for rho, right? Where rho equals to 0 is going to satisfy rationality and stability, right? What this implies is that if you make rho sufficiently small, we're going to have a solution that satisfies both rationality, right, and stability, all right? So we're going to let this rho r be the value, right, of rho that satisfies rationality, and rho s be that for stability. Now in the paper, you're going to see that we can actually work out this rho r and rho s in closed form based on the R4 and R6, their definitions, as well as the definition of this model reward, right, that we have, okay? Now, this is a visual illustration of the various incentives and the reward scheme that we have. It's described in the theorem 1 in our paper. We assume all the n parties, right, they are going to work together. This entire box, right, contains solutions which are feasible, right? That's, I think it should be R1, right? And efficient, right? Now you can see here that rho, which is the trade-off parameter, it can range from 0 to 1, right? And this rho sharply fair solution is going to satisfy fairness, right? That's highlighted in yellow, okay? Now when rho is 0, like I mentioned earlier, right, this is no longer fair, right? Every party gets back the same model, or gets back the same model which is trained on everyone's data. It ignores the parties' different contributions in terms of the value of the data, right? And as a result, this solution is not fair, okay? Now, the other thing you can observe is that when rho is sufficiently small, we can have stability and rationality, right? When you make it sufficiently small. Now, in particular, over here, right, you can see that if you set rho to be smaller than or equals to rho s, you're going to have a stable solution, and stability actually guarantees rationality, right, because they overlap, okay, here. Now, we kind of desire solutions in this shaded region, right, this small shaded region here, right, that's because it can satisfy all the various incentives that I've mentioned earlier, all right. Of course, except this group welfare. So as rho decreases from 1 to 0, right, you can see that now what you're going to see is that the rewards, they will deviate further and further from the sharply fairness, right? Because remember, when rho is 1, it is a sharply fair. But as you decrease rho, it's going to deviate further from sharply fairness. Or put differently, it is less proportional to the sharply values that you have seen earlier, right? Now, as a trade-off, even though when you decrease this row, it decreases the proportionality to the Shapley values, what you're going to see is that this group welfare is going to improve, right? In other words, everybody is going to get a better and better model, right? Until you reach this stage where everybody gets exactly the same model that's trained on everyone's data, all right? So that's the trade-off that you see when you adjust this rho. Now, we don't consider rho to be less than 0, right? As it is unfair. And we don't consider rho to be more than 1 because it doesn't really improve any of the incentives that we already have. Now, in some scenarios, the sharply fair solution, which is the one smack right here, right? It may be naturally rational, all right? When 1 is less than rho r, right? When 1 is less than rho r. So actually, you know, rho r can be more than 1. Okay, now the last part of this whole deal is that we're going to look at how do you realize these model rewards, right? Because we have a reward mechanism or reward scheme, right, that incentivizes collaboration. Now that we have figured out what are the values of the model rewards that each party should get, how do you realize such a model, right, so that it can be passed to each party? Now let the decided reward by the incentive mechanism that we have previously be Ri star, okay? Now to realize Ri star, the central party will need to select or derive data, right, from the aggregated data of all the parties, all right? Now one direct solution, right, is to simply select a subset of the aggregated data of every party, all right? But, you know, this method is, you know, not very practical because it requires us to consider an exponential number of possible subsets of data, right, to give. Also, right, it gives a discrete or finite solution space, right? It may not include the decided reward, okay? So to avoid the above issue, what we instead consider is a solution that involves noise, right? Because it's a simpler continuous optimization problem. Now, what the intuition behind this is simply the following, right? We inject noise, right, with an optimized noise variance, eta I, right, only to the other party's data. Why do we do that? Right? If we inject noise to the other party's data, it's going to reduce the amount of information, right, in the other party's data that's being conveyed to this party I itself, all right? Now note that, you know, for party I itself, we don't add noise to its data, right? Because we want the party to get all information from its own data, right? There's no reason why you should add noise, right, to your own data, okay? So that's how we do it, so that it can be the value, we'll be able to realize the value of the model reward decided by the incentive mechanism previously, right? Simply by adding noise. Now we're going to make some brief comments about the experiments. Now this is an experiment that looks at the role of this rho, right? This trade-off parameter, right? Now early on in this, that earlier diagram, that visual illustration where we decrease a rho from 1 to 0, right? In here, you're going to see decrease rho from 1 to 0, right? Now what's happening is that the reward, remember I mentioned previously, the reward for any party, right? And if this party doesn't have the maximum Sharpey value, right, you're going to see that they will increase, right? Remember that when rho is 0, everybody gets the model that's trained on everyone's data. That's the highest possible model reward, all right? And as a result, you know, as you decrease rho, everybody will get a higher value of model reward. And as you decrease rho, you can see that, or just now I recall that I mentioned the group welfare improves, right? Because the model rewards improves, right? Until everybody gets the same model, right? Trained on everyone's data. And when you improve the group welfare, right, it can satisfy stability, right? Which is this rho S value. Once you cross that, it's going to satisfy the stability incentives, right? The grand coalition is stable, okay? Now we have also shown on this page, right, that on this slide, that, you know, this is a plot on information gain. When the information gain improves for a certain party, this information gain corresponds to the value of the model rewards that it received, right? Now, when the information gain improves, now over here, this corresponds to the predictive accuracy, right? One way of measuring that would be the mean negative log probability, MNLP here. Now, as information gain of each party improves, you're going to see that the predictive accuracy is going to be better and better because this is a loss, right? The loss decreases, okay? Now, from the plot, we can also observe that the reward difference, right, between parties, as rho decreases, the reward difference is going to narrow, right, until you get the same model. And as a result, for parties with larger Sharpe value, for example, the party that's going to get the best possible model, right, they need to be altruistic as you decrease rho, right, or they need to be generous. Why? Because they don't gain as much as the others from reducing rho, okay? Now, this is not really a significant drawback because regardless of the value of rho, the party with the largest Sharpe value, it always receives the most valuable model as reward, all right? So it's not really losing that much, okay? All right, so now for the other experiments, I'd like to refer you to our paper. These are our key findings. Now we have evaluated our approach, right, on the diabetes data set, as well as this Californian housing data set, where you can imagine different estate agencies collaborating, right? And we have, run it on Bayesian regression models, such as the Gaussian process model, or a neural network with a Bayesian linear regression as the last layer. Now, the general observation is that parties that receive model rewards with higher information gain, when a smaller rho is used, and if they have a larger Sharpe value than the others, right? And this usually translates to better predictive accuracy, right? As you have seen just now. Now, to wrap up, now our goal is to get parties to collaborate and share data, right? To achieve this goal, there are a few desired incentives, right? Rationality, that's the one where I want a model that's better than my own, so that I want to collaborate with others, right? Then the exchange should be non-monetary, right? In this line of work, we allow it to be non-monetary because instead we focus on every party getting back its reward. It'd be great if we can offer privacy to every party as well, all right? Now, our solution satisfies all these incentives, right? This is stability, fairness, rationality, one that's non-monetary, but we have not looked at privacy yet. We're gonna leave it to our future work, right? We have something that's going on right now. So now in this case, each party, such as a hospital cluster, is gonna get a model reward with better accuracy, all right? Now, our other contributions include proposing how do we do data evaluation, right? How do we value a party's or a coalition's data? And we have done that through the notion of information gain on the model parameters, right? Given the data that's provided, all right? Now, we have also proposed to inject noise in using this optimized noise variance, right? To control and realize the reward value that is decided by the incentive mechanism that we have. So for more information, please refer to our papers. Now, for the next work, right, I'm going to look at the rights to be forgotten, right, in machine learning, specifically that of unlearning, all right? And this is a work with Fong, that is my postdoc right now, and Patrick Jallet from MIT. It's published in NeurIPS this year, which is not too long ago. So what's the motivation? So, a few years ago, I installed this certain app, right, to search for a new apartment, yeah, because I wanted to move to a different place. So, after doing so for a few days, this app was kind of automatically showing me ads of apartments that really suit my taste bud, right, in terms of the location that I am looking for, whether it is freehold, whether it's next to the coast, etc., right? And this really totally freaks me out. Then I started thinking that it must have learned my preferences, right? Specifically by training a machine learning model with my search data. So I immediately tried to uninstall the app, right? And at that moment, you know, I was hoping to kind of see an undo button, right? That allows me to undo the learning with my data, right? And you know, this brings me to this second part of the talk, right? How can we unlearn a trained model, right, from the data that I want to erase? Okay, I'm going to give you you know, a high level intuition to this work. All right. So now in a machine learning application, right, we often want to train a model, right? Want to train a model using a data set. However, you know, after training a model, we may think about wanting to erase a small amount of data, right? A small amount of data. Now it can be personal data of a user, right? The personal data of user creating an application like what I've done, right? And you know, the hope is that I can exercise, you know, my right to be forgotten, okay? Because doing so, right, it helps us realize the true notion of personal data ownership, right, which is enforced by this General Data Protection Regulation in EU, right? In Singapore, we call it PDPA, right? Personal Data Protection Act in Singapore, right? Now, there can be another motivation, right? It could be that the small data to be erased can be some malicious or erroneous data, right? Think about cybersecurity, adversarial learning, right? Suddenly, you know, you realize that for the past few weeks, your model has been under attack, right? But you have unfortunately already ingested this malicious data, and the model is trained with that malicious data, and hence is performing poorly. Now, in this case, how can I unlearn, right, this data that I want to erase over this past few weeks of malicious data, all right? Which is what I've said, right? Now, besides erasing the data from your database, if you still store the data, right? Now, the key question that we ask ourselves is how can we remove or unlearn the effect of this data to be erased from the trained model? Now, a very naive solution is to simply retrain, right? You can think about retraining, right, the data from scratch using all the remaining data that you have, right? And not include the data you want to erase, okay? But as you know, this can be very inefficient. Why? Because the remaining data can be a lot larger than the one that you want to erase. Or in certain circumstances, you know, if that company doesn't have enough storage space, then you're bound to erase some of this data, right? That will be lost, all right? So now instead, you know, when we talk about machine unlearning, we rely on what? We rely on the model that is already trained and the data to be erased, right? Making use of these two components, right? We want to perform unlearning to get the unlearned model, right? That's what we want. So this, you know, the goal of this machine unlearning is simply the following. Look at the retrain model, right, that you can retrain using the remaining data, and the unlearn model where you have only access to the train model and the small erase data, right? We want to be able to minimize the difference between the unlearned model, right, which can be done, the hope is that it can be done or computed efficiently, right? We want to minimize its difference from, right, the retrain model, right? However, you know, we have no access to the retrain model, of course, right, because you need to get it from the remaining data, right? So the aim is to minimize the difference simply by making use of the train model and the small erase data, all right? Now in this paper, we focus on Bayesian models, right? It's able to produce for you a prediction. On top of that, it can produce the uncertainty of your prediction, right? Or put differently, right, it produces distributions, right? In this case, we call it the posterior beliefs or posterior distributions of the model parameters that we're trying to learn, okay? And we are trying to minimize the difference between the two. Now, our main contribution here is to look at the notion of KL divergence or Kullback-Leibler divergence. Now, it's a measure of it's a measure of the difference, right, between distributions, right? In this case, our unlearned posterior and the retrained posterior, right? We're going to study how we can use this for the case of machine unlearning. Now, first we construct this thing called the evidence upper bound, right? I call it UBO, okay? It is a counterpart of this elbow, right? Which is the evidence lower bound. And both of this, or this term, or the evidence lower bound came from this approximate inference framework called the variational inference, all right? And we have a counterpart for unlearning, which we call the UBO, all right? Now, to elaborate, right, for elbow, which is the evidence lower bound, it is used to learn the posterior belief, right, given the data that you have, all right? So this is the part about learning, right? From the prior belief of what you know about the world, after you gather some data, it updates the prior belief to the posterior belief, all right, given the data. That's how we do inference, okay? Now, to compute this elbow, right, to compute this elbow, it consists of two terms. First, the likelihood term of the data, right? And the KL, or the KL divergence, the distance measure that we have between the prior and the posterior, all right? So what does maximizing the elbow mean? It means that we want to maximize the likelihood of the training data given the model parameters. And at the same time, we want to keep the posterior, right, to be close to the prior instead of letting it run away, all right? Now, on the other hand, for UBO, it has a very similar analogy, but instead what's happening here is that we want to unlearn, right, the posterior from the data to be erased, right? The data to be erased is here. We want to unlearn the posterior belief from the data to be erased so that it gives you this prior, all right? And how do we do it? Similarly, this UBO, right, it consists of the likelihood of the erased data and the KL term, right, that measures the difference between your posterior and the prior that you're trying to unlearn to, all right? Now, while we are trying to keep the prior that we've unlearned to be close to the posterior, right, minimizing this UBO means reducing the likelihood of the erased data, right? So we want the likelihood of the erased data to be reduced. Now, why would we want to keep the prior that we are trying to unlearn to be close to the posterior? If you don't keep them close, it might give you some form of catastrophic unlearning, right? Yeah, so we want to prevent that, okay? Now, for this notion of UBO, right, it requires you to use the exact posterior, right, given the full data, right? Or at least, you should have a very accurate approximate posterior belief, right, which is the one that is highlighted in blue. But, this requirement is often not, or it often does not hold in practice, right? So how can we unlearn an approximate posterior that is, something that doesn't correspond to the exact posterior, okay? So, our trick is to introduce a kind of threshold that you see as this dotted dash line, right? And reduce the effect of unlearning for parameter values in this region, right? These are the region where you have the approximate posterior belief to be very small, right? Now, to achieve this, right, we look at the use of this thing called the adjusted likelihood, or what we call the reverse KL, right? And, for more information about these techniques or tricks that we use, I like to refer you to the paper. And, we have empirically demonstrated our unlearning methods on, again, Bayesian models, such as the sparse Gaussian process model or the logistic regression model, right? For more information, please refer to our paper. So I've come to the end of my talk, right? So let's see, what do we do next? Suppose we can stop sharing.
Thanks, Prof. Brian, for the informative talk. It was really interesting. So now the floor is open for questions. So please do ask your questions by unmuting your mic. Additionally, you can also type in your questions in the chat box.
Hi, Professor Low.
Hi.
Yes, I have. This is Murari.
Hi,
I have a
Murari.
question. Yeah, so I have a question. So certain data might not be that might not be contributing to the prediction accuracy in the validation data, right? But they are still useful. Sometimes even the noisy data can make the machine learning model robust to certain type of data. So how do we evaluate those types of data? Like, it seems based on this paper, those type of data will be considered less valuable or non-valuable.
Oh, you're referring to the first line of work, right?
Uh, with
Uh,
the, yeah,
are you referring to the collaborative ML work?
sorry, yeah, it's for the first paper.
Okay. So now if I go into my data valuation method, right? So it is not really the case that, hold on. Now it's not really the case that it will treat all noisy data to be of no value, right? But instead, for data that is, you can imagine if it's extremely noisy, then, if you are able to capture the noise variance, right, using the model that you have, now information gain is going to decrease the value of information from noisy data, right? So the noisier you get, the value of information will be reduced, right? It's not as if the information will go to naught. But you can imagine as well that, if the data becomes extremely noisy to the aspect of random noise or to the extreme of random noise, then that provides no value.
Also, I have one more question. So aren't we depending too much on the machine learning algorithms which we are using, right? So the outcome of this valuation will depend on the type of machine learning algorithm we use. If you use a neural network, the accuracy might vary, right? The validation accuracy. If you're using regression model or some other SVM, suppose. So the validation accuracy will differ, right? There will be some variation. So basically, the valuation is dependent on the types of machine learning algorithm we use.
So certainly, because in this line of work, notice that we talk or we focus on the gain of information on the model parameters, right, rather than the validation data set. Because if we improve the belief or our understanding of what the true model parameters could be, it could improve, right, our overall prediction for any test query that we want, right, in the future. So in this, when we do so, then we are not specifically locking down on any validation data points that we are referring to, right? Why? Because this could cause certain bias. Certain parties may prefer certain validation data set more than others, right? So to eliminate this bias, we look at the overall improvement in the model parameters. But like you said, yes, the information gain, right? It is a very general concept that allows you to be computed for any model that you have. So different models will consider the value differently, right? So it depends on the model that you're using.
Yeah. So basically, you're agreeing, right? So that will happen if the underlying algorithm or the machine learning model change. Even if you use like logistic regression, linear regression, though, it will depend on the type of regression algorithm we are using.
Oh, that's right. Because different models are going to have different assumptions, right?
Yeah.
That they make about the data. So yes.
That is not in our control. Basically, that will impact the valuation or the information gain.
Right. Yeah. But of course, you can think about some kind of model agnostic way of data valuation, right? Yeah. Even if you compute it for a certain validation data set, I can imagine that, yes, you need to first ask what model are you using, right, for prediction.
Yeah.
Yeah. But certainly, yes, one good direction would be some form of model agnostic data valuation method.
Yeah, and also we are assuming that we already have all the data points, right, for which we want to make the valuation.
Yes.
So if additional data comes in future, so how do we adjust to that?
Oh, So I can only say that this is the or this work is the tip of the iceberg. It took us 2 years to come up with this work, and you know, there will be, in my opinion, there will be a lot of different research issues that we can tackle together, right, to move this community forward. That's certainly a very good question, right, where you have some form of what I call online learning. So how do we incrementally or iteratively evaluate the value of the data of a certain party?
Yeah. Also, I'm sorry, I have one more question. So
Go ahead.
I would like to interrupt, given that we have already overshot our time. Maybe you can take this discussion offline with him.
Yeah, sure.
So let's give others opportunity to ask questions if you.
Yeah, sorry, Brian, this is
Hi,
Mohan.
Mohan.
Hi. Excellent talk, excellent work, and I think very exciting work as well. I think, as you said, it has a lot of future potential.
That's right.
Now, about your first work, you know, in a hospital setting where presumably all the hospitals want to cure as many patients as possible, they may agree to a rho equal to 0, in which everybody gets the same highest quality model.
Right.
But in a slightly less altruistic setting, say banks sharing fraud analytics data,
right.
It may be in an interest of a bank to just give the minimum data and get the maximum quality model. In which case, basically, I need to just give, you know, I'm just being facetious, but one data point more than the one which gives the maximum data, so as to get the highest quality model.
Right.
And not give out all my data. So there could be kind of a behavior where everybody tries to give very minimal, hoping that he or she is giving just slightly more than all the other rivals to get the best model, then use my rest of my data internally to then further improve my model.
Right. Yeah.
So this does not encourage full sharing behavior yet.
Right. Let me see. I'm not sure if this will. So I think it ultimately depends. You know, there is a certain property in our work, right, that we look at, which is what I call the monotonicity property, right, when it comes to fairness. Right. Now, in this case, we made this assumption that if you contribute data of more value, right, it's going to give you a better model in return, right? So this is the property that kind of encourages everyone to share more. But of course, like what you've said, right? You know, the value of data diminishes, right? At a certain point, you know, if you contribute additional data, it could be that the value of the model that you get back in return may not be as much as what you get earlier, right? By contributing less. So again, this is another direction that is interesting, right? To explore. And to this point, you know, there's this part that, of course, I will say as a limitation of our work is this notion of the most powerful party, right? That means the one that contains or has data that's most valuable. So that's the one where, like I've mentioned in this work, they are going to see that the value of the model that they get may not be, you know, in the marginal sense, may not be as much as the weaker parties. All right. And as a result, I've mentioned the talk that they need to be altruistic. Yeah. So this is certainly one of the limitation that you know, we can think about how to resolve.
Yeah, I think more research, I think. Yeah.
Yes.
Thank you.
Yeah.
So I'm sure there are lots of questions following, but then given that we have already overshot our time, let us thank the speaker once again for this exciting talk. Yeah, and we hope all of you enjoyed the seminar as much as we enjoyed hosting you. So if you have any further questions, do please feel free to contact us on the email shown on the screen just now. And on behalf of Encrypt, I wish you a happy new year in advance, and do enjoy your rest of the year and enjoy your new year. Thanks for joining us.
Thank you. Right. Bye-bye.